Hello everyone, in this video I will present my M5 Final Hackathon project on responsible AI and model interpretability in credit risk prediction. My project is based on the home credit default risk dataset. The task is to predict whether a loan applicant will default, where target equal to 1 means default and target equal to 0 means repayment. But this project is not only about building a strong classifier, it is also about making sure the model is fair, interpretable, ethically responsible, and closer to production readiness. I'll organize my discussion into 4 parts: the problem and modeling approach, performance validation, responsible AI, and fairness, and finally, interpretability, ethics, and production readiness. First, this is a high-stakes classification problem because loan decisions directly affect access to credit. In this context, model errors have real consequences. If the model misses a risky borrower, the lender may lose money. But if the model incorrectly flags a reliable borrower as risky, that person may be unfairly denied a financial opportunity. That is why this task is especially appropriate for a responsible AI perspective. The data contains application level information such as demographic features, financial information, credit amount, annuity, employment related information, and external credit indicators. One important challenge is that the target is highly imbalanced, with far fewer default than non-default. Because of this, I did not rely on accuracy alone. Instead, I focused mainly on ROC, AUC, while also using PRAUC, precision, recall, and F1 score. For the modeling process, I first performed pre-processing. I handled mixed value through imputation, separated numerical and categorical variables, scaled numeric features, and applied one-hot encoding to categorical variables. I also removed columns with extremely high missense, especially some building-related features, because they would add noise and reduce model stability. Uh, First, for modeling, I used the two classifier. The first was logistic regression. As a plain fly model, I kept the baseline because it is relatively transparent and provides a useful benchmark. The second was XGBoost, which became my final model. I chose XGBoost because this is structured tabular data with nonlinear relationships and class imbalance, and gradient boosted trees tend to perform strongly in this kind of setting. To validate performance, I use both a holdout validation set and a five-fold cross-validation. This allowed me to evaluate not only the model's performance on one split, but also its stability across folds. I also compared multiple metrics instead of relying on a single score. In addition, I did threshold tuning rather than just using the default threshold of 0.5. In credit risk prediction, the threshold is not just a technical setting, it is also a business decision because it affects the balance between false positives and false negatives. The next major part of my project was responsible AI and fairness. In this assignment, responsible AI means the strong predictive performance is not enough. We also need to evaluate whether the model behaves fairly across groups and whether the workflow is transparent and accountable. To assess fairness, I audited the model across several meaningful groupings: gender, age, and income. Specifically, I used code gender for gender groups, days birth to derive age groups, and AMT income total to derive income groups. I chose multiple groupings because fairness cannot be judged from only one perspective. A model may look acceptable for one grouping but still show disparities in another. For fairness evaluation, I used group-level metrics such as selection rate, precision, recall F1, and accuracy through metric frame. I also included fairness-specific metrics such as demographic parity difference, demographic parity ratio, equalized odds difference, and the equalized odds ratio. These metrics help show whether the model's predictions or errors are distributed differently across groups. I also uh, I also included a simple mitigation uh, step. Instead of stopping at fairness measurement, I explored how threshold adjustment could reduce harm while still preserving useful predictive power. I think this is important because responsible AI is not only about identifying bias, but also about responding to it in a documented and accountable way. Another major part of my project was model interpretability. I improved interpretability at both the global and the local levels. For global interpretability, I used the feature importance and SHAP analysis. SHAP is useful because it helps explain not only which features are important overall, but also whether they push the prediction toward higher or lower risk. This gives a much clearer picture of model behavior than a black box probability score alone. For local interpretability, I use line to explain individual predictions. This is especially valuable in lending because decision makers often need to understand why a specific applicant was classified as high risk. I also use partial dependency plot to visualize how selected numeric features affect predicted risk on average. In addition, I included a counterfactual style analysis to show how changing some important features could change a prediction. This makes the model explanation more actionable because it shifts the question from why was this person classified as a high risk or what kind of changes are associated with lower predicted risk. These interpretability methods are directly connected to ethical decision-making. A model that influences credit assessors should not operate as a pure black box. Explainability improves transparency, supports review and governance, and helps detect whether the model may be relying too heavily on problematic practices. It also makes fairness analysis more meaningful because we can better understand the drivers behind group disparities. In the ethical analysis sections of my notebook, I discussed several risks. The first is disparate impact, meaning the model may create unequal outcomes across groups. The second is historic bias, because credit data may reflect earlier structural inequalities. The third is opacity, especially when a strong model like XGBoost is used without explanation. And the fourth is asymmetric error cost, because false positive may unfairly deny credit to people who would factual repay. Finally, I discussed the production readiness. A model that works in a notebook is not automatically ready for real-world deployment. In practice, deployment would require data validation, monitoring for model drift and fairness drift, collaboration checks, human review or sensitive cases, explanation logging for audit purposes, and version control for the pipeline and threshold settings. To conclude, my project showed that responsible machine learning in credit risk is about much more than predictive accuracy. I built and validated a strong classifier, but I also evaluated it through a responsible AI lens by auditing fairness, improving interpretability, reflecting on ethical risk, and considering production readiness. So the main takeaway from this project is that a good lending model should not only be accurate but also fair, explainable, accountable, and operational robust. Thank you.